Okay, so as a reminder, we're sort of transitioning away from the sort of typical synthetic organic chemistry that we've been discussing over the last probably, 10 chapters, right, where we're learning the reactions, applying them in synthesis. The latter part of this course, as a reminder, is going to sort of hopefully have a feel that's more a little bit of culturing you guys. There will certainly be knowledge to learn. I don't think it's necessarily going to be quite as intense, for example, as some of the other things that we've seen. But it's sort of more going to be a little bit of a survey type course feel that's going to expose you guys to the elements of the transition between synthetic organic chemistry and whether it's material science or biochemistry or medicine or things like that. And so today is going to be the first course sort of in that vein. And we're going to be talking today about carbohydrates and sugars. Okay, so starting with carbohydrates and sugars, I wanted to show this video. Okay, give us a second to load up. It's funny, I guess given how many Russians we probably have, crazy Russian hacker. So what we're going to be talking about today is carbohydrates. And again, this sort of name carbohydrates really stems from carbon and hydrates. So that's sort of where the name comes. And as we'll discuss afterwards, really we have an equivalent of carbon effectively and a certain number of equivalents of water, but you can sort of break it down into this. And one of these experiments, I decided to be a little bit safer, but this experiment that I'm going to show you today sort of shows how sugars really kind of are carbon and water to an extent. And what's important to recognize is when I show you guys this video, when I was a graduate student, I was TAing for a professor at Boston College. He actually did this experiment right in front of everybody. I didn't want to necessarily do that because I thought it would be a little bit dangerous.
Extinguisher close by, just in case. And in this experiment, we're going to do a crazy chemical reaction. Let's check it out. This experiment, we're going to need sulfuric acid and sugar. I got powdered sugar, but I don't think it matters what kind of sugar. And a couple of tubes, you know? Let's get to it. The reaction already started, so what we're gonna do is mix it up.
Yeah. This was actually done in the class that I was in.
And then you got so hot that it lost even more. What could it do that?
So basically what that is.
I'm going to try this again, but on a bigger level. So we're going to do sulfuric acid in there, and then
So anyway, so you're going to notice, and we'll see that again, so that is basically just charcoal and carbon, right? And what you're going to see sort of coming out of here is it gets very, very hot, and all the smoke that you see released is actually just moisture and water. So that's the carbon and the water. So you can sort of watch it again, you'll see it fizzing, and that's moisture, water. That's all moisture and the process it leaves behind.
It's just a statement, I feel. Okay, it's coming and coming.
So, and again, it gets bigger, right, because you're going
What
effectively...
do you guys don't say comments? What does this say? Yeah, comments are gonna go crazy. Alright guys, let me know what you think comments below. That experiment is really epic, but
Epic. Okay, so that experiment was very epic. So anyway, so that's going to be the rest of the class, right? Videos and stuff. It's a way to start this transition. So again, the idea behind that, while funny, and that guy clearly has personality, the idea behind that, right, in sort of the introduction to sugar chemistry, is that literally the name carbohydrates comes from carbon and sugar. And so really what we're talking about is molecules which have a certain amount of carbon, right, and then a certain amount of equivalence of water. And so that's where the name carbohydrates comes from. Certainly in an experiment that we saw, the sulfuric acid was effectively doing what kind of reaction? Dehydration, right, which we've seen in the past, right? We've seen alcohols dehydrate. That's exactly what was happening, and what's left behind after that dehydration is basically just that, right? Water and carbon, yeah.
So what's the dangerous about that?
Well, conch sulfuric acid, having it in front of a classroom, I think would, I don't know, I wouldn't want to be personally walking sulfuric acid down the halls of Brooklyn College into the classroom. So the overall process isn't that dangerous, but you know, when you guys work with sulfuric acid in a lab, right, you're working within a fume hood for a reason, right? Yeah. Why does acid stain? Acid doesn't stain your hands orange. Yeah, criminal minds. Yeah, no, there's no reason why acid would change your skin orange unless that was the chemical burn that you got, right? Unless it damaged your skin to a certain extent. But, you know, certain acids might, but I don't know, if you Google chemical burn, or if you guys ever get chemical burn, it's usually just like inflammation and red, and your skin will peel, and it's not like you become an Oompa Loompa, right? It's just... all right, anyways. Sugar, CN, and whatever, M. So literally it just means hydrated carbon. And so as we'll sort of see, again, there's going to be a couple of classes of these, but they'll all have this general same type of count to it. So some of these we will call, I'm just doing this wavy line, say one or the other. Okay, so on occasion what we'll see, and this is perhaps the most notable that we'll see, are sugars that have this general structure to them. So we'll have some number of groups here, right? And so clearly you can see at the middle, right, you've got water and carbon. On the ends, it's a little bit different, right? Here we have CH2OH, right? And so down here we have a carbon and H3O, and up here we have a carbon and OH. So if you just take one of these carbons and put them up there, you can sort of see that we have that same number, right? So we've got one extra proton down here from H2O, one less carbon up here from H2O. So anyway, so sugars that are of this form, right, are going to be called aldoses because of the aldehyde component to them. Okay, and occasionally you'll see an aldehyde-containing sugar. This will be primarily the majority of sugars that we see will have a carbonyl at one side, a CH2OH on the other side, and then sort of a series of carbons that are sort of sp3 carbons where you'll have a hydrogen and an OH to them. So that'll be one class of sugars that you'll see primarily. That's really what we'll focus on. But there are other classes of molecules that are also carbohydrates but instead of having an aldehyde, are in a slightly different oxidation state, or sorry, excuse me, slightly different. The carbonyl is in a slightly different place. Do that. You can have a ketone somewhere in there. Okay, so really the idea behind this is that these molecules have, and there, the idea behind these carbohydrates, right, is that you have these linear structures that are effectively fully saturated. So they've got oxygens at every single carbon, fully saturated, except for one carbon-oxygen bond, which is oxidized, right? Whether it be to the aldehyde or the ketone, right? So it's just one oxidation state up, right? Okay, and so if these are called aldoses and they represent aldehydes, you might be able to predict that these are called ketoses, right? So from ketones, because now it's got a ketone rather than an aldehyde. So this is a ketose. Okay, so that's just the sort of first general descriptor of them. Again, we are going to focus almost exclusively on aldoses in this course for the most part. Almost exclusively. Now, as you sort of noticed, and let me just do this squiggle here, because what this squiggle means is I'm not really defining which side is on the other. But as you start noticing how I'm drawing these molecules, right, I'm starting to get them back into structures that we've seen in the past, right, which are Fischer projections, right? And so Fischer projections, the idea behind Fischer projections, right, if you just remember, Fischer projections look like this, right? Right, these just sort of crosses, right? So anytime you see a molecule that's sort of a cross like this, this is a Fischer projection. And Fischer projections are almost never, ever used, with the exception of in sugar chemistry, okay? So sugars is really, specifically within stereochemistry, this is sort of more historical, I guess. When Fischer, Fischer, who began the work in this area, was working on understanding stereochemistry, is working on sugars. He didn't really have necessarily definitions for what sugars were what, per se, for example, but he was trying to illustrate the differences in the structures, and so it happened to be these types of orientations that they had. Again, this doesn't mean anything to you guys, right, just by itself, but as you guys have learned, there is a assumed three-dimensional property to a molecule like this. Right, molecules aren't T-shaped. Well, organic molecules generally aren't T-shaped. And as we sort of learned, the sort of bow tie trick, right, if we think about our dashes and wedges, when we see a Fischer projection, you start to do the dashes and wedges, and the way that I always think about it, again, because there's no rhyme or reason why they chose to draw it this way, right? This was just something that was created. So this is one of those unfortunate things that we'll have to sort of memorize and sort of remember. But I think the way to sort of remember it is the bow tie rule, right? Because you have this sort of bow tie looking like guy, and that's the way that you can sort of remember that on the sort of horizontal axis when you're looking at Fischer projection. The wedges, right, the ones coming towards you guys, are on the sort of horizontal. And so the bow tie rule is at least how I sort of remember that. Okay, so that's just a quick refresher to those. Now in sugars, we're going to be talking about these molecules, and primarily what we're going to be focusing on, we'll be drawing these a lot in terms of these Fischer projections, but this would be perhaps a good time to start thinking about stereochemistry, right, and revisiting the Fischer projections, okay? And we're going to start calling Fischer projections D or L, okay? Okay? When we call these D or L, right, there's going to be lots of different stereocenters to these molecules, right? But when we name things D or L sugars, what we're primarily focused on, right? And again, we're going to focus primarily on aldoses to sort of simplify things. But really, what we're talking about is the penultimate carbon, that very bond, with the final one in this sort of series. Okay. So if we have a molecule that has a whole bunch of OHs. We're going to name this D or L based upon that sort of bottom carbon right there. Okay. So to start thinking about this, one of the first things that we'll want to sort of do with this bottom carbon to refresh on stereochemistry is, start with what we know, right? And we haven't really learned D or L yet. But what we do know is R and S, right? So let's start with R or S. So in this molecule that I've drawn here, so with the sugar that I've drawn here, let's talk about what that stereochemistry is right there. So why don't you guys all start trying to sort of identify this? I'm hearing a vote for R. Okay, how do we do this, right? How do we learn, how do we identify something as R or S? Teresa. Right, so we start, guys, quiet. Guys, quiet down. So we're going to start numbering this based upon priority. Again, the priority is based upon the direct connected atom and the sort of priority of that atom, right? And so on this carbon, we've got two carbons, a hydrogen and an oxygen. Those are the first things bonded, right? And so the oxygen is first. We know the hydrogen is last, right? Because that's the lowest. And now we've got to decide between these two protons. Sorry, these two carbons, right? This carbon has an oxygen and two hydrogens. This guy has an oxygen, a carbon, and a hydrogen. So they tie at the oxygen. But next we move on to the carbon, and it's a hydrogen versus a carbon, right? So this is going to take 2. And this one down here is going to take 3. And then when we look at this, right, what we do, and this is one of the areas that I have a little bit of a pet peeve in terms of how people will come up with tricks to be able to quickly identify this, because then you have to remember those tricks. Really, at the core of any R and S configuration, you should just look at the molecule with the proton going back, right? So you should look at the molecule. What you really want to do is take a look at this molecule with the proton going back, right? And so if you look at this molecule, and in principle I'm looking at it from this viewpoint, right? With that OH going up and the proton going back, right? I'm going to have that 2 to my right. So I'm just going to define this one as 2, because it's that part. I'm going to define this as 3, right? And as somebody said, right, this is R. Right, and that's what somebody said earlier. And again, sometimes you guys can learn tricks to these, and certainly that could make your life easier to an extent, but I find that when you're learning these tricks, then it's a new trick to learn, and you can begin to confuse when you use some tricks in one time versus the other. Again, as long as you put that proton back, focus yourself in that general position, and then get the molecule, that would be R. Okay, great, so we have R, okay? And as it turns out, again, this doesn't really, there's no rhyme or reason behind this, but what D stands for is dextro, which, again, that's probably to 90% of you guys, dextro doesn't mean anything, right? But dextro is technically like Latin for right or clockwise, right? And so R would be dextro, so in this case this would be dextro. L stands for like levo, which is basically left. So at a certain point you have to just kind of remember these two, and again, if you sort of know, I guess, the Latin, that can help. I didn't know it, so I had to come up with my own way to remember these. And the way that I sort of remember D and L, to remember that D is R, right? To remember that R is D and L is S. This is just something that I came up with when I was an undergrad to help me remember this. Is that you can take that D and turn it into an R, right? And L, you can turn that L into an S. And that's just how I remembered D and L being R and S, and it worked for me, so maybe it'll work for you guys. But again, if you know the Latin, you can remember dextro or levo, then perhaps you can do that. If you can't, like I didn't know, this was again, I'm not big on tricks, but when I have no other way to remember it without learning Latin, I have to sort of use these tricks to remember it. So again, what we're talking about is the bottom carbon, in this case, again, whatever the sugar is called, you're not going to be responsible for memorizing the different names of sugars. If you need to know what glucose looks like, you can look up the structure. If you need to know what mannose looks like, or rhamnose, or whatever, you guys can look up the structure. So I'm not going to ask you guys to remember all these different molecules, but I think it's worth it to just sort of know that when you see these called D or L, they're generally referring to the sort of bottom stereocenter, and so this is kind of an opportunity perhaps to refresh on thinking about R and S and D and L. Okay. Yes?
Does D always rotate like this, right?
No.
Yeah.
What's that?
Says that dextrometry versus transport.
Probably not always. That's probably the bottom one. If it is, that might be the case, and it's completely coincidental then. It's possible that some of the early, so I'll double check this for you, but my understanding about rotational light, because if you guys remember, this is all about rotating light in certain ways or another. It is nearly impossible, people are still working on this, trying to figure out how one structure will rotate light in one way and predict it rotating in one way, and how another one can rotate in the other way, right? Because there's multiple different stereocenters in there. So the likelihood, maybe it's the case, but that would seem to be purely coincidental and be a little bit different than what I'm accustomed to seeing. But if you change all of these things up here, and somehow this one center down here, changing how the light's going to go one way or another, seems to be unlikely. More likely what happened is when you isolate the bottom part, that's the one that, if you just isolate that bottom part where this would be the aldehyde here, it's probably that one that rotated it one way and the other one that rotated the other way. So it's probably that fragment. But I could be wrong. But we can look into it. But yeah, it's what's that? Okay, yeah, okay. Good, I'm glad. Okay. Yeah, but that's one of those weird things, right? It's like a lot of the initial namings of things were based upon how they rotated light. So you're absolutely right. Like, it rotated it clockwise. They named it D, and they just got lucky, and it happened to be R in terms of how we think about it. But in truth, I don't know the history behind it, but my guess is R was probably then subsequently named afterwards, right? When they were deciding how to orient the molecule, they were like, oh, well, if you put this proton in the back and a number of these, we can call that R. That was probably before they actually had pure definition of what the actual structures were, because certainly the names were there long before we had concrete understanding of the RS type configurations for them. So, all right, so anyway, so that's just sort of getting back at stereochemistry. Now, in general, what we're going to start seeing a lot of, we'll get back to sort of aldoses. So you're going to see a lot of sugars that look something like this, right? Where we'll have on one hand the aldehyde, we'll have the other end the OH, and we'll sort of just change how we draw them based upon which side a hydroxyl is on one side or the other. I think thinking back to Gen Chem, sometimes you guys will like leave out a hydrogen or just like leave it blank, and that will represent hydrogen. Just draw all your hydrogens on these as well, just because otherwise to me it suggests a methyl group, right? Just because that's how we normally draw them. But if we have a molecule that looks something like this, right? When we have a molecule like this, we've been discussing a lot of sort of stereochemistry behind these molecules, and sometimes it's difficult to take a molecule like this and start to think about how this molecule might actually look like in 3 dimensions. Guys, can you quiet it down a little bit, please? Sorry, I'm having trouble focusing when I'm hearing people chatting. So this is sort of a molecule that in principle looks like it's 3 dimensions, right? Or it would be otherwise 3 dimensional. One of the difficult things to sort of do, I think, when we're thinking about sugars, and one of the perhaps challenges and skills that you guys might want to develop, and that you will almost certainly be quizzed on, whether it's on an exam or a quiz, is to take a molecule like this and perhaps draw it in a way that's more classical to how we're used to be drawing it, right? The Fisher projection, as I've sort of told you guys, really doesn't tell us that much in and of itself. Now, there's a couple different ways in which we can draw these sugars. And one of them, actually all of them, tend to take advantage of this fact that sugars rarely exist in this sort of linear form, right? We have seen in the past examples where hemiacetal formation is reversible, right? We rarely have hemiacetals, right? At least when it's 2 molecules. But it turns out that hemiacetals, when they can be intramolecular hemiacetals, tend to form fairly quickly. So there's a lot of examples of hemiacetals intramolecularly. Intermolecularly, less likely. They'll fall apart, perhaps due to entropic penalties and stuff being paid by having to keep those 2 together. But certainly in terms of intramolecular case, this could be the way. And certainly in sugars, this is the case, right? And if you start to think about, in general, again, we'll talk about 5-member rings as well, but just on the sort of surface, if we were going to form a ring here, right, the most likely ring that we would form would be the most stable, right? And as you guys have sort of learned, 6-membered rings are some of the most stable compounds that we have. So we'll see some examples of 5-member rings as well, but in the same way that aldoses and ketoses, we said primarily aldoses, in this case we're going to focus primarily on 6-membered rings as well, okay? And the 6-membered ring, right, is going to form 1, 2, 3, 4, 5, 6. It's going to form between this alcohol here and that carbon there. So there's going to be 1, 2, 3, 4, 5 carbons, right? And then the 6th member of that ring is going to be the OH. Okay? And so at this point, what we have to do, what we can sort of recognize fairly easily right off the bat, is that if we were to take this molecule and think about what it actually looks like, it's a sort of series of bow ties, right? The thing is that as this molecule is drawn, it suggests that it's forming up like this, right? But and so if it's forming up like this in terms of a ring, one of the sort of advantages to looking at a molecule in this formation is that when it forms up into a ring, right, everything that's on this side of the molecule is going to stay on that side of the molecule. Everything on the other side of the molecule is going to be on the other side of the molecule. The one difference here, though, is that this oxygen is forming the bond with this carbon. If we folded it up like this, it would be this carbon which would be coming in proximity with this carbon. So the only thing that we need to do, we can start to map this oxygen, hydrogen, oxygen as we sort of fold this up. But this carbon here is the one that we have to sort of account for and rotate, right? If we're going to fold this up, this alcohol wants to be here, such that when it folds up, it's going to come into proximity with the carbonyl, form that hemiacetal. At that point, then everything, even on this carbon that's on this side, will be on the same face as that side. Okay, does everybody understand that? Right? This is a series of anti-bonds. So it's sort of folding up like a crab. But as it's drawn, we want to have this hydroxyl forming there. As it's formed, it would be this carbon there. So let's rotate that. So this is one of these things that I saw people doing last semester, and they were screwing it up a little bit. And so I figured I would teach it this way, because I think that there was some mistakes that people were making. If you want to rotate this bond around, right, it's important that you start to recognize that when you move one bond, right, when you're rotating around, right, we can hold one thing constant. But anytime we're rotating around a bond, let's say if this is constant, If we want this A where the B is, then the B has to go where the C is, and the C has to go where the A is, right? I find that people a lot of times just switch two groups. And what happens when we switch those two groups? We change the stereochemistry, right? So if you're going to start to rotate around this bond, if you want to put that OH there, then you can't just put this group over there, right? If this is going to move here, if you want to hold all of this constant, like we did there, if you want to hold all of this constant, you're going to move this here, then it's carousel, right? This has to move here, this has to move here, this has to move there, right? Does that make sense? It should make sense, right? But I did see last semester a lot of people trying to do this, and they were just switching bonds and changing the stereochemistry. So just recognize, if you're going to do that rotation that we want to do, then you got to rotate all of them. Or if you hold one constant, rotate the other three. Okay? And so for the bottom one, again, we can push that back. Again, we want to move that OH there. So what's going to happen is, over on this side, we're going to have the H2C. Right? We're going to have this here. Just so it's unambiguous. Right? So this is going to move here. This is going to move here. And then this is going to move to the other side. Okay? So now this is the molecule that we're going to sort of draw, right? It's going to be, now when we fold up as a sort of molecule, again, a series of antibonds, now this OH is going to come in proximity to that carbonyl, right? And that's going to be the ring. And so now everything that's on this side of the molecule is going to be on one side of that six-membered ring. And everything that's on the other side will be on the other side of the six-membered ring. Does that make sense? Okay. So let's go ahead and try and draw this. This is where being able to see in 3 dimensions can be helpful. Now again, if you have some trick at this point, hey, maybe it'll work for you. What I would try to do is visually, again, the same with doing RNS, I would try to visually, without any tricks or rules, it's going to be tough at the beginning, but try to fight through the urge to be like, oh, when it's this, I put them on this side, or when it's this, I put them on this side, because then you're likely to make mix-ups. I think if you visualize this, consider sort of what it looks like, and then try to fold it up. That might sort of help you to an extent. So if I'm going to take this molecule and turn it into a six-membered ring, we can start in what's called a Haworth projection. Okay? Haworth projection is going to be, we'll start from there, and then we'll move to the chair and discuss sort of axial, equatorial, and so forth. But in a Haworth projection, what we have is sugars that look to a certain extent something like this. I haven't put the groups there per se, but it's a six-membered ring. It represents that six-membered ring, right? And we're not really going to define, we're going to kind of draw it flat. It doesn't obviously look like that. But it does kind of look like this would be the representation of if we simply took these bonds and made the connection, right? But again, we're not going to define axial, equatorial, anything else like that. We're just going to define on that six-membered ring which sides are one group of molecules on and which sides are the other groups of molecules on. And so to a certain extent, we have to position ourselves mentally within this structure, right? And so I've sort of already done that to a certain extent with the oxygen. Maybe you'd have an easier time if you put the oxygen there. Sometimes that's a little bit easier. Maybe I'll do that. That's sometimes easier to do. Okay? And what I'm going to do is I can start numbering these. So I'll say 1, 2, 3, 4, 5. Okay, so this will be 1, 2, 3, 4, 5. Okay? And now, I'm just going to start really quickly with the 5. It doesn't really matter. We'll discuss this in a moment. But the 5, okay, the position of 5 is going to be this carbon. This carbon doesn't have any stereochemistry, right? So when the OH attacks it, it could really go one way or the other. Okay? So this is a position we'll talk about a little bit more later on. This is called the anomeric. And what I'm going to do is, for now, we'll discuss it a little bit later, but for now we're just going to sort of give it a squiggle. Know that it could be one way or another, right? Because, again, that's a hemiacetal, it's reversible, we can discuss that mechanism, right? But when this attacks that carbonyl, you can have two possible stereocenters, and those can go back and forth, again, because of the hemiacetal. We've seen this in the past. So now what we have is the position of 1, right? Now, this is more of a sort of curiosity question to you guys. At 1, either on the top, we're going to have an H, and the bottom, we're going to have the CH2OH, or it's going to be vice versa. So I want you guys to sort of try to take a look at this molecule, and I'm just sort of more curious to see, and don't feel bad one way or another, whether this group here is going to be on the top or the bottom. If this is going to be up here, don't say anything yet. It's going to be here or here. Okay, I'm going to take this molecule, mentally bend it, wrap it together. Think about this coming towards you as I wrap it. Okay, by show of hands, everybody spend a couple seconds looking at that. Show of hands for how many people think this group is going to be going up. Show of hands for how many people think it's going to be going down. How many hands for people that have no idea? Okay. So, I got a little bit of everything, as I sort of anticipated. And this is one of the things where I would really urge you guys to keep trying if you have to build a model, say for example, to see it, because I do recognize this can be challenging. But if I take this molecule and rotate it, and if you think about this proton being my thumb, and you think about this guy, my finger over here being the CH2OH, and I fold it, right? You notice it's going to be going down. Right? So I'm going to take this guy, I'm going to wrap it, put that OH here, that group there. And again, that takes practice, that takes visualizing. If you have to get a model set, you can do that, right? But this is coming towards us. We're going to wrap it together, proton up, OH going down. Okay? All right. So, okay, so that's a great suggestion. So the alternative way that we can do this, that was just brought up, that I actually really liked a lot, is that we can take this molecule and perhaps do an intermediate step where we draw it horizontally. Okay? If we take this molecule, draw it on the horizontal, and then think about it coming together. The question is, can we do that? That may be easier for some, might be not. But let's go ahead and try it. So the bond that we're making is this one here, right? So if the bond that we're making is that, then we want the OH on the left-hand side, right? So this is going to be on this side of the molecule. The aldehyde is going to be on the right-hand side of the molecule. So if we go ahead and we draw this molecule and think about it from this carbon here, right, so this is going to be on our right side. Well, hold on.
I think from what I do is also the alcohol group is going to be on the right. And the aldehyde is going to be on the right.
Well, the aldehyde is on the right.
Yeah, but when I drew horizontal, it works out that alcohol starts out on the left, not on the right.
Okay, we'll take a look at it afterwards. But again, you could imagine what's happening is when you're drawing this molecule, right, this proton at this position is coming down. When you're rotating it down, the proton is going to be coming towards you. The OH is going to be going that way. And then once you've sort of seen that, then you can sort of follow around there and perhaps do that around it. But the point is that once you've sort of gotten this position, again, if you have to go through some intermediate, you may want to get out a model set or whatever so you can start seeing this. Again, this is one of the reasons why I think it's important to work on this stuff and not simply go with tricks. But now that we've got this, again, the OHs will all be on the same side as this proton. This hydrogen will be up here. SOH will be here. And that group will be there, okay? And so this is sort of the three-dimensional representation of this molecule. Or at least a closed version of this molecule. Okay? Now the position that we haven't defined, right? Yeah?
Would it depend on how the OH attacks at first? How everything is up or down?
Well, no, because I'm not following. Nothing here would change.
Doesn't matter how the OH attacks.
Well, how the OH attacks is going to change how this group is.
Just that.
Just that group. Certainly I could just draw the molecule upside down and put that OH in a different position. But once I have, now if you're looking at it a different way, right, and you say, for example, had the anomeric carbon here and started the one over here, then yes, certainly. But once I've picked where that OH is, and I've picked where the rest of my carbons are, and I picked my anomeric, then everything has to be on one side or another, and I have to figure that out. So the way that I first drew it, maybe that doesn't necessarily work for you, but as long as you can get to a way to draw it, if it's easier for you to see it from an opposite standpoint, then go ahead and get that. But make sure that it actually works, right? I think that's one of the concerns, is that when you guys, I think it's always good if you can come to a understanding of something yourself, learn it yourself to an extent, but the challenge sometimes in organic chemistry of trying to do that, it's good, you kind of want to do that to an extent in organic chemistry, as long as you're doing it right? You got to make sure that you're not doing something wrong during that process, which can be, I think, one of the challenges. Okay, so now, within the context of the anomeric carbons, there are a couple different stereocenters that you could sort of have, and again, the OH could be going sort of one way, or it can be going the other way. And I always hated this nomenclature. Again, I mean, it's fine, it is what it is. But again, it is nomenclature, and I'm obviously not a big fan of nomenclature. But there's two possibilities here, right? The OH can be going this position, as I've shown there, or and again, I'm not a big fan of nomenclature simply because it requires memorization oftentimes, and I'm obviously not a big fan of memorizing things. Because I personally don't have a great memory. But clearly the OH could be on the top face of this molecule, or the OH could be on the bottom face of this molecule. And the same reasons that we give anything names, right? Just to sort of know what one thing is or the other. We give these things names as well. And the way that we name these is based upon the orientation of the OH, right, relative to the adjacent hydroxyl. So in the closed form, what we really refer to it is sort of whether or not, is that part I always forget? Let me just double check, because I always confuse these two. Okay, so this is sort of just one of my pet peeves, so I apologize with alpha and beta. Alpha and beta terminology is one that organic chemists use a lot, and it's often very well misused in organic chemistry. So anytime I start hearing people say alpha or beta, I inherently cringe. But within sugars, there is a defined reason why something would be called alpha or beta, and I just want to double check because I thought I So as it turns out, if they're on the same face of one another, we're going to call those sort of alpha. And if they're on opposite sides of one another, we're going to call them beta. The reason why I'm a little confused, I didn't really think about this that much, but I thought it was the other way around. But I just checked the book, and I guess I was mistaken. So again, it's obviously not super important, but certainly when molecules are made to be, say, for example, polysaccharides and so forth, as we'll discuss, they can sort of build up on each other in different ways. But again, there is this name for them. I don't care that much about the nomenclature, but you can read that in the book. Again, if they're on the same face, I guess they're alpha. If they're on opposite sides, I guess they are beta. All right, let's get on to some cooler stuff, aside from nomenclature. Okay, so much like sort of sugars, I think there's one of the cool things about sugars is something that bucks the trend to what we've seen previously. And this is going to be taking these forms that we've had there. I'm going to take it to a subsequent level, yeah.
Well, you said it's alpha?
That's...
Here it says...
Yeah, because I thought A was anti, right? Because it's like alpha is anti. Sorry, I got caught up.
Oh, you have... because it gets mentioned in chapter 16.
Oh, here's the... No, because alpha's same side. We'll get back to it. Let me double check, because this is why I'm a little bit flustered right now, because as I was reading this morning really quickly, I had it in a couple meetings that sort of caught me off guard. But what I had seen, I thought was, because I had this idea in mind, oh, A means, alpha means anti, we can think about it that way. But then as I was looking at this, it clears different. Certainly this isn't something that's that important to me. But I'll double check just so you guys know. But again, it's going to be based upon proximity to other parts. I don't even think I taught this last year, but people kept asking about it, so I meant to look into it this morning. But the more important thing is, again, as you guys know about me, hopefully by now, naming things, nomenclature is obviously not something that's important, in part because we can draw it, right? I don't need to know whether something's alpha or beta, or, it's more important that I can draw it, I can see it. We don't talk organic chemistry, even though the names could in principle have importance, but you can't really get at the heart of the conversation without actually drawing it. And so if we start to think about this anomeric carbon here, we can sort of recognize that this molecule, right, we've drawn it sort of flat, but in reality, right, this molecule is not going to exist in this way, right? What's it going to exist as? A chair, right? And once we draw it as a chair, right, the overall we start to bring in an additional element to it, right? This is going to be equatorial, axial, sort of substituents and everything else like that. And so if we were to take this molecule and we were to draw it as, say, for example, a chair, right, as is currently drawn, right, that OH is going to be axial, right? So this would be 5, right? At 4, it's up, so up would be equatorial. Number 3, this is also going to be down equatorial. 2, it's going to be up equatorial. And 1 is going to be down equatorial. And so, as you see that I've drawn this in its current form, pretty much everything on this molecule is equatorial. Now, the thing about sugars, right, is a little bit different than other compounds, is that it's not as clear. Like, you may look at this molecule and say to yourself, oh, the molecule is definitely going to be in this conformation, or perhaps, as we'll discuss in a minute, with the other sort of group in the other position. But the thing about these molecules is, when you have sugars, let's take a look and draw it in the alternative chair conformation. Right? So if we do the chair flip, right? So now I'm just going to put this in equatorial again. We'll get back to this one in a minute. But now everything is going to change. Everything is going to be equatorial. And so in general, this move to this move from everything equatorial, again, ignore the anomeric carbon for now, this move from everything equatorial to everything axial would generally be a sort of a bad thing, right? Except what is it about sugars that is kind of interesting about them, right? Is that you've got all these alcohols sitting around here. Once you put, right, what is the reason why, say for example, two methyl groups would never want to be, why these would never want to be axial to one another? Sterics, right? You put two CH3 groups really close to one another, you create this steric strain. In the case of alcohols, what happens when you put those two H's near one another? You can begin to get additional favorable interactions, things like hydrogen bonding. Right? Sometimes even in an aqueous environment, sometimes water can even help participate in things like that. You can see the same thing, say, for example, here. Right? So it's very difficult in sugar chemistry, so this would offset any potential steric demands. So it becomes very difficult. I'm never going to ask you guys to predict the most stable sugar conformation, right? I think that you can draw a couple of them, maybe you could rationalize why one might be better than another, but it's very difficult. Unlike what we've seen in the past with chair conformations, this added component of hydrogen bonding can often make it sometimes difficult to predict which type of orientation that sugar is going to be in. So occasionally you will see molecules drawn, say for example, in this way, and maybe it's that conformation that they would like to otherwise react with. So that's sort of that. Now, but something else actually comes up here, and that's that in both of these cases, we have these anomeric carbons. We haven't really defined them here. Yeah.
Wikipedia says that alpha is 6 and beta is 10.
Which is what I said, right? Yeah. I'm going to double check that because I was reading it before class very quickly, and then I had a couple meetings, one sort of very last second. So I didn't have a chance to confirm it, but I had this A being anti, and that's why when I checked the book, we'll double check. Again, it's far from that important. You know, nomenclature with me is not something that I care about too much. But again, you guys should, whatever. So anyway, so something really cool about anomeric carbons, though, is that you have these positions here. And that adds an additional component that is kind of interesting. And even outside of sugar chemistry, sometimes you see it quite a bit. And that's that when you have cyclic hemiacetals, like let's say, for example, let's put something that would want to be equatorial, like a ketyl group, right? Certainly these molecules so you can certainly see in instances where hydrogen bonding, there could be things that might illustrate, but there's an additional component here, which is this anomeric carbon. And I think on the surface, even absent from those potential hydrogen bonding networks that you guys saw previously, in a simple molecule like this, where all we have is a T-butyl group and we have a sort of anomeric carbon here, your intuition, based upon what you've learned in the past, might tell you right away that this molecule, right, is the most stable molecule, right, because of the fact that OH is in an equatorial position. But it turns out that one of the fascinating things that was really borne out within studying sugar chemistry is that oftentimes this one is more stable. Okay, so this is another interesting aspect about sugars. This is absent from this hydrogen bonding network. And the reason is something, and I'll bring up an example in our lab where we saw this take place. So this is more stable. So previously we saw the hydrogen bonding. This is a phenomenon called the anomeric effect, and I'll show where we witnessed this in our own chemistry in my lab. But I like this. I like teaching this. I don't think this is in your book. I think your book might actually suggest otherwise. Your book's wrong. Anomeric effect is something that's real. And it says that oftentimes it's basically a way to explain why very often you will get acetals and they will have a propensity to adopt this conformation as the thermodynamically most stable compound. It's not a kinetic argument. This is actually more stable than this here. And one of the reasons I like teaching this is it allows us to begin invoking sort of viewing sigma stars, viewing orbitals, right? Thinking about orbitals at a level that perhaps we haven't in a while. Now, when you guys learn substitution chemistry, SN2, right, perhaps you guys maybe discussed sigma stars, right? Perhaps it was taught in some other way. But in principle, what's happening, say for example, when you do when you have a nucleophile attack this molecule, right? Every bond has a bonding orbital, right? If it has a bonding orbital, then it also has an anti-bonding orbital. This is what we often call the sigma star. You've seen this from time to time, right? It's sort of sigma star. And so when we see, say, for example, nucleophilic addition through an SN2 transformation, what's happening is the electrons from the nucleophile, right, they are starting to donate through this process. They begin by donating into this empty, low-lying empty orbital. Right? So the electrons begin to be pulled into this sigma star. The lower energy the sigma star, the most likely the electrons are going to want to go into those sigma stars. In the case of this is a little bit different, but this molecule also has sigma stars to it, right? Anytime you have an electron, electronegative atom bonded to electropositive atom, oxygen bonded to the carbon, what you have is fairly low-lying sigma stars, these molecules as well. This carbon and oxygen, this is your sigma star here. Okay, so this is the sigma star for this carbon oxygen. Okay, everybody sees that? Jutting into the molecule. This is the sigma star of this carbon oxygen. Okay? Now, what do you guys notice about, say, for example, these axial lone pairs right there? They're in the same plane, right? Are there any lone pairs that are in the same plane as this? No, there's a bond, right? There's a bond, there's not electrons. So in principle, again, going along with this sort of hyperconjugation, what's this full, yeah, this is almost full lone conjugation, right? Like lone pairs, not just a proton, not electrons within a bond, but actually lone pairs back bonding in a way into that group there, creating a sort of extreme resonance form. Obviously, this is a very extreme version of this, right, where we've actually fully broken that bond. But if you take a look at a molecule that looks like this, what a typical OH bond would be, it's when you look at sugars, when they have this sort of anomeric effect, the bond is actually much more lengthened. Again, based upon this back bonding into there. So there's evidence that suggests that, again, it's not fully broken per se, but that ability to back bond, or to have that conjugation with that sigma star, lengthens that carbon-oxygen bond, okay? This is the anomeric effect. I think it's really cool. I think given your understanding of chair conformations, you can sort of appreciate this, and it's a pretty cool phenomenon. And what it also allows me to do is give you an example of chemistry in our lab where we've seen this, which I think is always a nice way to draw home concepts when they actually happen right upstairs, right? And this was something that an undergraduate in our group did. Actually, one of the first papers that we ever had in our group. It was Alberto Munoz. Was working on this molecule here. This is a gamma hydroxybutanolide. It might look familiar. Okay. And what he did, right, and maybe this will be a mechanism question for you guys to consider on your own, but we'll discuss the end game product of this. What he found is that if you have aldehydes, specifically aromatic, AR means aromatic aldehydes, so benzene derivatives and stuff like that, and really strong acids. So he was actually using triplet acid in this case, or actually TMS triplet, but just a really strong acidic source. So TMS is kind of like serving as the proton in this case. What he would get in these reactions is a molecule that looks something like this. there's your carbonyl. Okay, make sure I get this right. Okay, so this was the molecule that he generated. And he generated this as a single diastereomer, okay? And you look at this group here, and this isn't really a sugar per se, right? But it is sort of chair-like in nature, right? And if you look at the two aromatic groups, you might be able to predict that those would otherwise be equatorial in nature. But what's kind of interesting, right, is that over here, right, you have, that's supposed to be an oxygen up there. It's horrible. Ugh. I'm running out of chalk. But again, it's sort of chair-like in nature, and we actually had crystallographic data of this. We got a crystal structure that showed this. This is the only diastereomer that we got. This overall process is reversible. In fact, we can exchange out one of these aldehydes only. We can treat this with this molecule. But you'll notice in addition that what's axial? Right, that carbon-oxygen bond, right? Now, the size of, say, for example, an oxygen bond versus a CH2 or a CH group really isn't that big, right? You wouldn't expect huge preference based upon steric effects. But the fact that we only get a single diastereomer has to do with the fact that, again, likely that we have this anomeric effect going on, where the carbon-oxygen single bond is actually axial, right? Which we argued was likely because of anomeric effect, right? Let's try that at home. And we can talk about it at another time. So that's a good, tough mechanism problem. Let's try it at home. You're trying to figure it out. So anyway, so again, try the mechanism at home, but the point is I'm not going to go through the mechanism because it's not necessarily that relevant, but it could be a good mechanism problem for you guys to try. It's perhaps a little bit more an advanced one. You can go and look at the answer on the paper, which you can find on my website. But again, the important point is it's the thermodynamic product. Two aryl groups equatorial, which you would expect based upon what you guys have learned, right? The big groups want to be equatorial rather than axial. But when you put those two equatorial, this additional carbon here, that oxygen is axial, right? And again, invoking anomeric effect argument. All right, so that's my intro to carbohydrates. Over the next 10 minutes, what we're going to do is we're going to talk about some chemistry and reactions of carbohydrates. Many of them are reactions that you guys have seen in the past. I would expect you guys, specifically in some cases, which will be hopefully recognizable reactions that are simply now in the context of sugars. And then what I will do next week, so what I'll do today is I'll summarize a bunch of reactions. And then what we will do next class, we have an exam Monday? Monday. Ooh. That's a double bond oxygen. So it's like this double bond here. Okay, so we'll start getting into some of the reactions with the remaining time today. And then what we will do is we will, next class, I will introduce you guys to sort of sugars in the context of sort of like immunology, for example, and you guys know about like AB blood types and things like that, and how those will talk about that and how sugars are related in those situations. But today we'll discuss a little bit about chemistry. Yeah, you have a question? Okay. Okay, so yeah, I guess we should, huh? Yeah, okay, next Wednesday I'll get to tell you all those good things. So now's a good time to just mention. Do we have class Monday? Oh, sweet. Oh. Oh yeah, spring break. I know. Yeah. Yeah, no, I knew that. Yeah. guess I need another coffee or something this morning. So yeah, so we'll do a review next class. Come with questions. So then it would be the Wednesday after the Wednesday. So this is your cumulative organic reactions exam. So you're going to be responsible. This is going to be the summary, effectively, of organic synthesis for you guys. So certainly there are things that you haven't been tested on yet, which are recent, and so certainly like those type of reaction questions that I've asked you guys will probably be based upon a lot of that stuff. So amines, cross-coupling, organometallic transformations. But yeah, I mean, this is going to be the sort of cumulative chemistry in general. So again, it will be there will be more of this other chemistry, but like that we've learned recently. I do want you guys to know, again, back to we quizzed you guys on it, but it may come up again. Understand sort of stereochemistry of Diels alders and co-plays and rearrangements and those kinds of things. But nothing today. Nothing that we discussed today. That'll be more for the final. So yeah, so everything up through last class. Okay, so just a couple really quick reactions, and I guess we'll probably then, since it's going to be a while before we come back to this, we'll revisit these again later on. But I just want to throw these up here because hopefully you guys will recognize that this is chemistry that you guys have seen in the past, right? So a lot of times if you have sugars, right? A lot of times if you guys have sugars, what you guys will have is lots and lots of sugars that will be sort of bonded together, right? And so I'll leave out everything else here for now, but you can imagine, right, if you have, say, for example, O-Me or something like that, and then somewhere around here, say, for example, you have an OH, right? There's chemistry where these two could, for example, begin to form bonds together, right, and begin to get polysaccharides and a lot of other molecules. From a reaction standpoint, you guys might be able to sort of see that this reaction is something you've seen in the past. It's effectively it's kind of like you guys have seen in the past. This is formerly an aldehyde, right? And you guys have seen lots of reactions in the past where carbonyls have condensed on various other alcohols. And formally, that's all this reaction is. So if you mix these two together under acid, and certainly this is a question that would be fair game for the exam because it's chemistry you guys have seen in the past, right, from a mechanism standpoint. How does this and this react together? And again, there's a couple different mechanisms that you can draw, right? You could imagine a mechanism whereby you go through the aldehyde, or you could imagine a mechanism where you go through the oxocarbenium, right? And so one way that we can imagine drawing this, right, there's a couple different mechanisms, but one way that you could imagine drawing it would be to first protonate that OH. Generating that carbocation, right, after you lose water, followed by minus water. So protonation minus water, you're going to generate oxocarbenium, right, which can be stabilized. Right, and then when you're at this, what's going to happen? Right, the other alcohol is going to happen, right? So you could also draw it through the aldehyde as well, right? There's an alternative mechanism, and you guys can draw either one, right? But what's going to happen here now is that you're going to get something like this, where after a few steps, you're now going to get to right? And again, this isn't the best example of it, right? Because perhaps you could have other things over here. But the point is that sugars can form in this kind of way. And what you call this, right, is sort of a glycosidic bond formation. So this is the glycosidic bond. It's basically an anomeric bond, and it's called a glycosidic linkage. Okay, and I'll show you examples of this in a synthesis later, I guess in a couple of weeks. I'll show you that. So again, that's chemistry that should be familiar to you, right? It should look very similar to you. Another reaction that should be also very, perhaps, relatable, right, is what do you think happens if you take this and you treat it with sodium borohydride? You guys think what happened if you took this molecule and you treat it with sodium borohydride? What is this? What's this in equilibrium with? Right. In conjugate, right? So there's this tautomeric form where it's the aldehyde, right? And so as it turns out, if you take a sugar and you treat it with something like sodium borohydride, right, you can actually reduce this. So it's important to recognize that right, what will happen is you'll actually reduce it. So if you reduce this, just as you would with any aldehyde, right? This kind of stuff can happen. There's also other reactions that you guys have seen, right? Again, because sugars have lots of diols to them, I'm just going to throw two more reactions up there, and we'll discuss them more later on. So we'll discuss this more next class or next. If you have syn hydroxyls, right, and you treat this with periodic acid, right, HiO4, what do you think happens? Yeah. And so we'll discuss this one a little bit. This actually has some ramifications in terms of identifying proteins. 1, 2, 3, 4, 5, 6. Right? And you'll get to the aldehyde. So I don't know. Anyways, we're out of time. So just a reminder for two things. First of all, I made corrections to those who asked for regrade request forms. Someone did get a lower grade. Which is just a reminder that actually understand what the question you are asking is and what the right answer is before requesting a regrade request form. It was the question that this person was asking. He said, I know that I got points wrong because of X. And actually, we didn't take off points for that X. We had taken off points for something completely different. And so, nothing I could do there, right? The law is what it is, so I had to take off some points from that person. Some others you did get, there was some legitimate questions, so some of you did get extra points. I wrote down explanations for everything on the sheets, so if you did ask something, you'll get the reasons back to you in writing from your recitation instructors. Anyway, come with questions next class, okay?